Hello, my name is Luke Clausen, BICSI U.S. Western Region Director. Thank you for joining us for Choosing the Right Fiber for Your Enterprise and Data Center Network, presented by John Camino. John is Senior Manager, Multi-Mode Optical Fiber Product Management for OFS. His background includes product management, offer management, sales, and engineering. John has published numerous articles in technical publications and presented at multiple technical conferences. He has also participated in TIA and IEEE standards activities. John is a member of BICSI and obtained his RCDD in 1994. Ladies and gentlemen, please welcome John Camino.
Hello, and thank you for joining me here today. I'm John Camino. I'm the Multi-Mode Optical Fiber Product Manager at OFS. I'm here today to talk about enterprise data center and local area network fiber selection. The agenda I'm going to follow today, I'm going to cover a discussion of the fiber types that are used in the enterprise, talk about enterprise applications, both LAN and data center, and then talk about specific data center applications, and then close with a few recommendations. So with that, I'll start with this introduction into some basic fiber technology. There are two types of fibers that are used in enterprise networks today, multimode and single mode. Both have a 125 micron outside clad diameter, but multimode fiber has a larger 50 micron core, while single mode has a smaller 8 micron core. Multimode fiber operates at lower wavelengths, from 850 to 940, while still supporting some legacy 1300 nanometer applications, while single mode fiber operates at a higher wavelength range, between 1310 and 1625 nanometers. Multimode's larger core gives it some advantage in the ability to use lower cost sources and therefore keep total systems costs down for short reach applications. A single mode fiber, as the name implies, only allows one mode of light or one path for the light to travel down the fiber. This eliminates any what we call modal dispersion, or different modes traveling at different rates of speed through the fiber core, and thus allows tremendous transmission capability or capacity over very long distances. Multimode fiber, on the other hand, allows light to travel along many different paths or many different modes, hence the name. In a multimode fiber, you are going to get some pulse spreading due to these modes traveling at different rates of speeds through different parts of the fiber. You can see when looking at this fiber that light traveling directly down the center of the core has a shorter path than light that's traveling along the core clad interface and being reflected from side to side. If they all traveled at the same speed, then the light traveling down the center of the core would arrive far earlier than light taking the longer path. We compensate for that the different distance traveled by grading the index of a multimode fiber. You'll see here the refractive index profile of a 50 micron multimode fiber, and you can see that the index of refraction is highest at the center, that is at the radius 0 of the core, and lowest then at the core clad interface. Light traveling down the center of the core in the area of highest index of refraction then travels at the slowest rate of speed, while light that has to go further being reflected along the core clad interface will travel faster because it's going through a lower index area. Ideally then, whether the light travels directly down the center of the core or is reflected along the core clad interface, it will still arrive at the detector or the far end of the fiber at the same time. Unfortunately, as we all know, there's no such thing as every fiber being perfect, and there is some pulse spreading. So you start out with a pulse width T, and then at the detector, you'll see a pulse width that's slightly wider, or KT. We measure how well we're able to grade the index of that fiber using something called differential mode delay. We measure that by injecting light at different spots along the core in 1 micron steps, beginning at the center and stepping out to the core clad interface. You can see when looking at the OM3 fiber on the left that light traveling at the center of the core at radius 0 arrives slightly earlier than light traveling nearer the core clad interface. And thus you have a wider pulse width. On an OM4 fiber though, if you look at the fiber on the right, you can see that all the way from 0 out to 25 microns, that pulse, irregardless of what path it takes, arrives at nearly the same time. That pulse width then is much narrower than the OM3 fiber, and you can space the input pulses much more closely. That means that you have a much higher information carrying capacity in that OM4 fiber, and the bandwidth then is much higher. If we look at the definition of different multimode fibers in the standards, you can see that there are a number of documents and organizations in the industry that define multimode fiber. The two most commonly used associations are the TIA in North America and the ISO-IEC organization that's used worldwide. One thing that's happened in the past 2 or 3 years is that there's been an alignment in nomenclature or naming between the two organizations. And they've adopted what was originally in the ISO-IEC 11801 document, where you had OM1 through OM4 originally, fibers defined, and now you see OM1 through OM5. That wasn't the case previously in TIA, where there were different documents for each fiber type. But now they've got a single document that has all the common 50 micron multimode types in TIA 492 AAAF, and you see the common OM1 through OM5 designations. One thing I want to point out is in the cabling documents, the ISO-IEC 11801 and the TIA 568.3 documents, you'll note that OM1 and OM2 fiber types have strike-throughs. That's because those fiber types are no longer recommended. They're included in the appendices of both of those documents and can be used to support legacy applications, but they're no longer recommended for new installations of multimode fiber. A couple of other things to point out here are the attenuation at 850, specifically the cabled attenuation at 850 for OM3 and OM4 fiber. TIA has defined cable attenuation at 3.0 dB per kilometer, while the ISO-IEC document spells out a 3.5 dB per kilometer requirement. But the primary difference between OM3 and OM4 and OM5 fiber is shown on the far right, where we talk about the effective modal bandwidth, or the laser bandwidth of a multimode fiber. That laser bandwidth is really the information carrying capacity of the fiber. And you can see that the 2000 megahertz kilometer requirement for OM3 fiber, 4700 megahertz kilometer bandwidth requirement at 850 for OM4 and OM5 fiber. And then for OM5 fiber, there's an additional 2470 megahertz kilometer requirement at 953 nanometers. One thing that I wanted to show in this presentation is the continued growth in multi-mode fiber deployment worldwide. You can see from 2010 through 2025, there's been significant growth in the deployment of multi-mode fiber. Most of us here in North America may see that there's been a very little growth, that it's a mature market for multi-mode fiber, and that's been true in the Europe market also. But in China, there's been a significant growth in the deployment of multi-mode in their hyperscale data centers. One other thing that I'll point out, and I'll refer back to in a later slide when I talk about single mode fiber, is you'll note that there's about 8,000 FMM of multi-mode fiber deployed, roughly speaking, every year. And that's at the peak, obviously. So just if you keep that number in mind, 8,000 FMM or 8,000 fiber megameters are deployed annually in worldwide. If we look at the North American market, we can see how the market has changed over the past 20 years. In 2001, the vast majority of fiber was OM1 62.5 micron fiber, and only about 10% of the fiber was 50 micron OM2 fiber. In 2004, we start to see the deployment of laser optimized OM3 fiber. These are the fibers that were designed to support laser optimized applications. We see that grow rapidly then through 2009, 2010, when OM4 fiber becomes standardized, and we start to see that fiber growing in volume. We move all the way now to 2021 then, and you can see that now we're at nearly 90% OM3 and OM4 fiber, and only 10% of the fiber is a combination of OM1 and a very small amount of OM2 fiber. So it's almost a mirror image of what started in 2001 and where we are now in 2021. What drove that migration to laser optimized fiber? Well, this chart with the adoption or the same fiber mix data that was shown on the previous slide is overlaid with the adoption of some standards. And you see the 10 gigabit Ethernet standard being adopted in 2002, which was the first major laser-based multimode operation that really called for laser optimized fiber. It didn't get deployed widely until later in the 2008, 2009 timeframe, but you started to see the installation then of OM3 fiber. The OM4 fiber again started in 2010, and then in 2011, you saw the adoption of 40 and 100 gigabit multimode standards. OM5 was standardized in 2016. We got another 100 gigabit standard in 2017, and then the 400 gigabit standards that were drafted in or adopted in 2020. So as each of those speeds became standardized in Ethernet, we saw an increase in the adoption of laser optimized fiber. I will note, because I'm sure someone has a question, why don't we see OM5 here? OM5 hasn't been broken out yet by the Burroughs report. We expect that to begin in the very near future. Some of the recent advances in multimode fiber have been around the capability to support multiple wavelengths or wavelength division multiplexing. WDM has been implemented in single mode fiber for a long time, but only recently have we seen that being done in multimode fiber operations. Multimode OM3 and OM4 fibers are optimized for a single wavelength for 850 nanometers. OM5 fiber, on the other hand, is designed for operation across a window of wavelengths from 850 to 940. One thing, if you'll remember the requirement of 4,700 megahertz a kilometer at 850 and 2470 at 953, you may say, well, that's not the same bandwidth. But I'll note that it's the total bandwidth of the fiber, which also has another component of chromatic bandwidth that is a natural function of the fiber and increases as you go to higher wavelengths. So the combination of modal plus chromatic bandwidth of an OM5 fiber is equivalent across that entire window. Graphically, you can see the requirements in this chart where the circles show that there's a 4,700 megahertz kilometer bandwidth requirement for both OM4 and OM5 fiber at 850 nanometers. There's a 2,000 megahertz kilometer requirement for OM3 and the 2470 megahertz kilometer requirement for OM5. You can see that there are also lines drawn on this chart. Those lines are for guidance to transceiver manufacturers who are building devices that operate in between that 850 and 953 nanometer range. So they want to know what kind of bandwidth they can expect from an OM5 fiber or an OM4 fiber at, for example, 910 nanometers. And you can see that if the total bandwidth of the fiber of an OM5 fiber is equivalent across that range, that the OM4 fiber doesn't have that same ability to support multi-wavelength applications. Similarly, the OM3 falls off across that entire range. So you can see that they have much lower bandwidths at that 953 area. How does a wideband or an OM5 wideband fiber work? Well, if you remember, the OM3 and OM4 fibers are designed for single wavelength laser-based operation. So in a duplex transmission, you'll see one transmit fiber and one receive fiber, and it will operate at 10 gigabits, 25 gigabits, and today up to 50 gigabits, and soon will be up to 100 gigabits per second. When the first 40 gigabit standards came out, though, to increase the bit rate, we went simply to multiple fibers. So instead of a single fiber carrying 10 gigabits per second, we had 4 fibers carrying 10 gigabits per second for an aggregated 40 gigabits per second. An OM5 fiber, on the other hand, instead of using multiple fibers, will use sources with different wavelengths and transmit over the same fiber, carrying that same bit stream over a pair of fibers rather than 4 pairs of fiber. So you have basically 2 times or 4 times the speed, depending on the number of wavelengths that you use. Some of the key advantages of multimode and multimode fiber VCSEL-based systems are driven by the source that's used, a vertical cavity surface emitting laser, or VCSEL. VCSELs are very low in cost, and they're very low power consumers. So that means that from an operational perspective, you have an advantage. And if you look at data centers today, where you can have tens of thousands or in hyperscales, 100,000 servers, you realize how important it is to have lower power consumption. Multimode fiber's larger core means that you don't have to align that source and detector with the fiber as precisely. So your alignment costs are less. When you make 2 fibers together in a connector-based system, your alignment tolerances aren't as tight as they are for a single mode system. So all those things provide for a lower cost system. However, one of the key advantages of a multimode based system are the fact that it's more resilient to contamination. If you look at the chart on the lower right, you can see that about 90% of network problems are created by contaminated connector interfaces. The larger core of a multimode fiber means that you're not as susceptible to that contamination. Moving now to single mode standards, we see the same ISO IEC and TIA cable standards, IEC 11801 and TIA 568.3, but there are different fiber standards that define the fibers themselves. On the left, I've talked about the TIA fiber types. You can see the single mode inside plant, single mode indoor-outdoor, and outside plant fiber types. You'll note that in IEC, there's only two fiber types that are defined: the inside plant, OS1A, and the outside plant, OS2. However, TIA has incorporated one additional fiber type, what they call indoor-outdoor. You can see that each of these fiber types differ primarily by the attenuation at 1310, 1385, and 1550. The inside plant cable has the highest allowed attenuation because those lengths are typically shorter, where the outside plant, because the lengths are longer and the attenuation budgets may be more stretched, has the lowest attenuation requirement. Indoor-outdoor then is somewhere in between the two. If you're more familiar with the carrier or fiber to the home market, you might be more familiar with the ITU designations, where instead of attenuation, they talk more about the fiber's bend resistance. You may have heard about G652.D fiber, which is a standard single mode fiber, or G657A1 fiber, or A2, or B3 fibers. And you can see that, as I noted, those are designated more by their bend resistance. And you can see for a A1 fiber, you can have a 10 millimeter bend radius and a 3/4 dB attenuation allowed. Whereas with a B3 fiber, it's a 5 millimeter radius and a 0.15 dB max allowed added loss. Those B3 fibers used primarily in customer premise applications where you see a lot of very tight bends going around corners. And they're the ones that you see all these demonstrations of fibers being looped around tight corners in a hallway, or in some cases, I think you've seen demonstrations with nails and things like that. So those are the fibers that they're using in that environment. I put this chart up on single mode cable production so that you can get an idea in terms of how much fiber gets deployed worldwide on the single mode side. And you'll remember when we talked about multimode, the top number in the upper left was 8,000 FMM. Here on the single mode side, you're talking more like 700,000. So it's nearly a 1:100 ratio of multimode fiber deployed compared to single mode. Single mode fibers used in all long haul metro and things like inner data center applications where links are longer. And as you know, as many of you may know, we're seeing very large fiber count cables being used in some of these applications where we're talking about 3,000 or almost 7,000 fibers in a single cable. One other interesting point just to note is that, again, here, China is the dominant market for single mode fiber. They've been very aggressive in deploying fiber over the past 10 years and continue to do so over the next 5. You can see that North America and the European markets are growing, but they're nowhere near the same volume levels as China is. The key advantages of single mode fiber are the fact that it has nearly unlimited bandwidth. From an enterprise perspective, you can almost assume that it does have unlimited bandwidth. Single mode fiber can support much longer link lengths because you're operating at higher wavelength ranges. The cable attenuation is much lower. You don't have the modal dispersion issues, so you can go much longer distances than you can with a multimode fiber. From a fiber perspective itself, the fiber is much cheaper because you have a single step index. You don't have the graded index where you have to very precisely monitor the index of refraction of the fiber all the way through the core. What makes single mode more expensive, though, for short reach applications is the connectivity. Remember, I talked about core alignment and how important that is for a single mode fiber when you have a much smaller core. And the transceiver costs are also much higher because you can't use a VCSEL-based system. I'm going to talk now about enterprise applications. And we'll start out with the traditional enterprise local area network. You can see in this application the typical building on the left where you have a fiber riser from a main telecom room going up to each floor, or possibly you have multiple rooms on a floor, but you're linking those typically with a multimode fiber because those are shorter links, less than 100 meters, less than 200 meters. And then you have out in the horizontal, typically a copper cable infrastructure. I showed some fiber on the second floor there. There are some applications where fiber to the desktop or fiber to the wireless access point is used. But in general today, in most offices, you see a copper-based solution. In the campus backbone, because those links are longer, typically 500 meters and greater, you see a lot more single mode fiber deployed. Again, single mode's designed to support longer link lengths, and multimode is really not capable of supporting very high speed links over long distances like that. One thing that we are seeing is the incorporation of additional devices onto what was traditionally a datacom network. So we're seeing, we keep hearing about IoT, but we're seeing building automation devices being added onto the network. We're seeing access devices. We're seeing security cameras. So there are a number of devices. All these things are being added to the traditional local area network and being carried over Ethernet. Another way to implement a local area network in an enterprise is passive optical LAN. Passive optical LAN was originally deployed in fiber to the home, or fiber to the MDU, fiber to the multiple dwelling unit, but now has been modified in some cases to support fiber in the enterprise. This is a single mode fiber solution, and it uses a centralized switch that then is deployed, and splitters are used in the floors to support multiple four-port access units that are then linked by copper to work locations or access points. Again, this is a centralized, you have your electronics centralized in this architecture, and then you're simply doing passive splitting at all these different points throughout the enterprise. It's popular in some vertical markets specifically. There have been a lot of installations on military bases and some in hospitality networks. I'll move up now to talk a little bit about standards and what's traveling, or what speeds are being used in enterprise LAN and data center networks today. I start out with the gigabit Ethernet speeds at the top, the 1000 base SX and 1000 base LX. People have been deploying gigabit Ethernet in their networks for a long time, and I'll show you later, they're expected to continue to do so. Gigabit speeds have been very popular for workstations. And then you also see the passive optical network 1000 base PX. One note in the IEEE designation, the S in the 1000 base SX typically implies short reach. The L in LX or L implies long reach, and the P is passive optical LAN. If you look, you can see that gigabit Ethernet was supported out to at least 550 meter link lengths for OM3 and OM4. But I'll note that that standard has been around for a very long time, and that 550 meter link length is really based on the use of OM2 fiber. Most transceiver vendors, cabling infrastructure vendors will support up to link lengths of 1 kilometer or more for SX. Then we move to the 10 gigabit speeds, the ones that I had in my chart showing fiber deployments. The 10G base S, 10G base L, these are all single fiber pair applications using one wavelength, going out to 400 meters on OM4 for the S and 10 kilometers for the long reach. So 10 kilometers on single mode, 400 meters on multimode fiber. I'll also note that there are many infrastructure vendors that will support up to 550 meter link length for 10 gigabit Ethernet. There's a column that I've got here that talks about optical modulation, and you'll note that as the speeds go up, it's pretty linear with the modulation rate is an NRZ modulation. So it's a non-return to zero, on-off type signal. So the light's either on or it's off. There aren't multiple levels. So you'll see 10G NRZ, 1G NRZ, 20G NRZ, and then you'll see different rates as we go to higher and higher speeds. But I just want to point that out because in future charts, we'll start talking about more complex encoding schemes. Once we get up to 40 gigabit Ethernet, you see both the SR and LR standards that go the 100 meters, 150 meters on OM4 and 10 kilometers on single mode fiber. But you also start to see some multi-source agreement or proprietary solutions in this table. These 40G SWDM and 40G BiDi solutions supported a duplex or two fiber 40 gigabit per second link. And you can see that they used either 4 wavelengths in the SWDM solution or 2 wavelengths in the 40G BiDi solution. Those are not standardized, but they've been widely deployed. You'll also note there's a single mode solution, a 40G parallel PSM4 or parallel single mode solution using 4 pairs that could go out to 10 kilometers. Then we get to the 25 gigabit speeds, 25G base SR, 25G base LR, and then the latest passive optical network standards, 25G G base P and 50G base P. These will go either 10 or go up to 20 kilometers and use either 2 or 4 wavelengths. One thing to point out about these passive optical network standards is they all operate over a single fiber and typically use 2 wavelengths on the same fiber, one to transmit and one to receive. The data center architectures have evolved as we've moved from what you see here, a hierarchical structure where you had a server linked to a top of rack switch, and then a tiered switch above that, another tier of switches above that, and then going through routers. This worked well when you saw a request come in from the internet and it was routed to an individual server to answer the request. However, today, due to virtualization, that request is often routed to a number of different servers. So we've moved to a flatter architecture where at this edge aggregation or leaf level, you can talk to just about any server in the network. So you don't have to go all the way up through multiple tiers to communicate between servers. This evolution will continue as we go to higher and higher speeds. We'll see this top of rack architecture give way to a more centralized switch location. On the left, you see the traditional top of rack architecture where you had a switch located at the top of the rack and it was linked to servers using either copper direct attached cables or active optical cables. This rack was typically pre-configured, so when you installed a data center, you simply rolled the rack in and bolted it to the floor, and then you simply had to tie racks together. In this new architecture, it will be somewhat similar, but instead of a top of rack switch, what you'll have is a patch panel. And you'll have all these server links cabled up to the patch panel, so you can still bolt that to the ground and do all your cabling rack to rack. However, the cabling is going to be optical because the links are going to be longer. You want to be able to support 30 to 50 meter link lengths. So you're going to migrate to an optical solution. And as you do that, then you're going to go from patch panel to patch panel when you install the data center using an optical link. We're doing this in order to, because as we migrate to 100 gigabit servers, these servers require a tremendous amount of power and have to dissipate a significant amount of heat. And you can only do so much of that in each rack. That's going to limit the number of servers in a rack and really makes the top of rack architecture inefficient. You don't have good port utilization. So this middle of row or end of row switch architecture then allows you to utilize all the switch ports and still makes for an efficient installation. We move now to some of the higher speed, hyperscale, and some enterprise multi-mode data center standards. And you can see how we're moving now from speeds that we were talking about 1 and 10 and 25 and 50 gigabit to now 100 gigabit standards, 200 gigabit standards, 400 gigabits, even 8 gig. And at the very bottom, we start talking about 1.6 terabit applications. With these 100 gigabit solutions, you see the 100G base SR4, which will go 100 meters on OM4. And then you start to see, again, multi-source agreement and proprietary solutions, the 100G SWDM4, the 100G BiDi solutions that will go 100 meters on OM4 and 150 meters on OM5. You'll note, though, that we now move to a 50G PAM4 encoding scheme. That means instead of a simple on-off signal, light signal, you now have multiple levels of light that are being detected. So instead of only having on or off, you have choice of 4 different levels of light being transmitted. This doubles the data rate that's transmitted in a bit periods. or in a certain time period. So instead of 25G, you're now operating at 50G. That allows things like 50G base SR4, 100G base SR2, and 200G base SR4. You also see 400G base SR8 and 400G base SR4.2. These are the first 400 gigabit standards then. And you can see that 400G base SR4.2 is a standardized solution that uses 4 pairs of fiber and 2 wavelengths. So it's the first wavelength division multiplexing application for multimode fiber. You'll also note that it supports a 150 meter link distance over OM5 and only 100 meters over OM4. So it takes advantage of that additional bandwidth capability that OM5 gives you out at those longer wavelength regions. Standards that are currently under development include the 100G base VR, 200G base VR2, and 400G base VR4, and the corresponding 100, 200, and 400 gigabit standards that are SR. If you'll recall on the last slide, we talked about supporting short, very short 30 to 50 meter link distances for fiber to the server. And that's what the VR application is designed for. It's the first time that we've really developed a standard that's specifically to support server-based applications, that short 30 or 50 meter link distance. That V stands for very short. So you then see that in study group, we have an 800G base SR8 that's being considered. And then also being talked about are some of the multi-wavelength applications for 400, 800, and even 1.6 terabits. I want to touch a little bit on 400G base SR4.2 because it's the first multimode application that takes advantage of OM5 multi-wavelength capability. It uses the same 4-pair infrastructure that's been used for 40G base SR4 and 100G base SR4, using the 4 outside fibers in a 12 fiber MPO. It operates at 2 different wavelengths, 850 and 910. And as the bi-di or bidirectional name implies, you see the light traveling in both directions on the same fiber. So it'll go one direction at 850 and the other direction at 910. On the single mode side, there are another list of data center standards. The 100 gigabits per second, and here again, you see the MSA 100 gigabit PSM4, 100 gigabit CWDM4. You'll note that these are in between the 100, 150 meter reach, short reach multimode solutions, and go to 500 meters for the parallel single mode 100 gigabit solution, and 2 kilometers for the CWDM4 solution. That was really in response to hyperscale customers who wanted to go 500 meters, but didn't want to have to pay the price for a 10-kilometer transceiver. They wanted something that would go shorter distances and didn't have the robustness that was needed to go 10 kilometers. These are both MSAs that were developed in response to those requests. You'll notice that there's a standard LR4 10 kilometer standard. And then as you get to 200 gigabits per second, you see that they do start incorporating parallel single mode in 200G base DR4 going 500 meters using 4 fibers. The FR4 that will go 2 kilometers, and then the old traditional LR4 that will go 10 kilometers. Similarly, on 400 gigabits per second, they've got an 8 wavelength solution for 400 gigabits that will go 2 kilometers, and then the LR version that will go the 10-kilometer reach, along with the DR version that goes 500 kilometers. And they're doing the same thing at 800G, parallel fibers, and then multiple wavelengths going either 2 or 10 kilometers. Multimode fiber modules continue to be widely deployed. One of the things that, if you go back 5 or 6 years, there was a lot of talk about silicon photonics eliminating the need for multimode and that everything was going to be single mode based. But you'll note here in this light counting market study, you can see that they can project that multimode fiber transceivers, even at the speeds of 25 gigabits and higher, will continue to be deployed throughout the study period. It's going to continue to grow through 2025. Even back in 2016, you see that single mode modules exceeded the number of multimode modules, but multimode modules continue to grow throughout the entire time period. Also wanted to note, in the enterprise and in networks in general, I mentioned the 1 gigabit and 10 gigabit networks that were still being installed. And this gives a lot of credence to that. You'll note in 2021 that 1 gig and 10 gig modules still combined outsell everything else. They're still the majority of modules that are shipped. Even going out to the end of the period in 2025, they make a significant portion of the modules that are shipped into the market. So while we see an adoption of higher speeds, especially 100 gigabit and then later 400 gigabit modules, there's still a large number of lower speed 1 gig and 10 gig modules being deployed. If you look at the enterprise itself, light counting says that 90% of the modules shipped in 2020 are still going to be 1 or 10 gig modules. So you see that in the enterprise, we're still seeing large deployments of these lower speed modules. The technology adoption rate isn't the same as it is in hyperscale. Obviously, there are exceptions. There are financial companies that use very high speed networks similar to hyperscale. But in general, the enterprise market has not migrated as rapidly to the high speed networks as hyperscale networks have. So in closing now, I'll just talk a little bit about recommendations and what I'd suggest you might consider when you're selecting a fiber for your next network. Single mode fiber can support all link lengths and speeds, but there are some considerations that you have to make. Yeah. Single mode's the most cost effective. In fact, it's the only solution for long links. For links 500 meters or more, single mode's the choice for high speed networks. But the optoelectronics, the transceivers are going to be more expensive than they are for multimode. Single mode power consumption is typically higher than it is for multimode. And then last, and maybe the most important from an operational perspective, connector cleanliness is a much bigger issue for a single mode fiber installation. Yeah. Single mode fiber is the fiber of choice for intermediate or long links. In enterprise applications, campus environments that exceed 300 or 500 meters, single mode fiber, as I say, really is the only choice for those high-speed networks. Some legacy applications will continue to use multimode fiber, and we see that. In-building applications, typically much shorter, are supported by multimode. And enterprise data centers are typically much smaller than a hyperscale data center and have much shorter links. So that's really where multimode shines. It's the fiber of choice for short reach applications. It's optimized for those applications, and with the power consumption and with the cleanliness advantages that multimode fiber has, it's still the fiber of choice for short reach applications. Thank you very much. I hope you enjoyed the talk. I won't be presenting this live, so if you have questions for me, my contact information is listed on the first slide. Thank you very much.